Just picture it. Hundreds of millions of tons of concrete, steel, and water working together every single second to hold back one of the most powerful rivers on Earth. The Yangtze River has carved its way through the heart of China for millions of years, and it's been both a source of life and destruction. But since the early 2000s, it's been controlled by the massive wall of the Three Gorges Dam, the largest hydroelectric power plant ever built. It stretches for over 2,300 meters across and stands 185 meters tall, almost the height of a 60-story skyscraper. Behind it, a reservoir stretching over 600 kilometers long and holding back more than 39 billion cubic meters of water. That's over 5 trillion gallons. Now this thing is not just big, it's a modern marvel. The Three Gorges Dam wasn't just built for show, it was built with two major goals in mind: stop the Yangtze's constant flooding and produce a huge amount of clean energy, and in many ways it's done both. When the last main turbine came online in the year 2012, the dam reached its full capacity in 22,500 megawatts, which is enough to power tens of millions of homes. In the year 2020, after an especially intense monsoon season, it hit a world record, generating over 111 terawatt hours of electricity in just 1 year. That broke the record set by Brazil's Itaipu Dam. But here's the thing about it. While it was built to protect and power, the dam now stands as a massive potential threat. The bigger something is, the harder it hits when it falls. If the Three Gorges Dam were to collapse, even partially, the effects wouldn't just be felt in the areas right below it. The disaster would reach across an entire region and ripple out through the entire world. Hundreds of millions of people live and work in cities scattered all along the Yangtze River. These include places like Yichang, right below the dam, and larger cities like Wuhan and Nanjing, farther downriver. These places are not just home to millions. They're packed with infrastructure, agriculture, factories, and key shipping routes. So now comes the big question: how could something so massive and so carefully engineered actually fail? What would it take? Let's start with the most basic problem: gravity and water pressure. That massive wall of water behind the dam, it's always pushing forward. The structure is built to handle that, but just barely. Like every major dam in the Three Gorges is constantly under stress. Over time, even small movements in the concrete or shifts in the foundation can start to cause problems. And the Yangtze River itself adds to the danger. It's one of the muddiest rivers in the world, and that matters. Every year, around 40 million tons of sediment move downstream. But with the dam in the way, a lot of that silt ends up piling up behind it. Over time, that buildup puts even more pressure on the base of the dam, making the water harder to manage and the structure more vulnerable. Now here's where things get more complicated. The dam sits on a fault line, not a super active one like in California or Japan, but active enough that earthquakes do happen. And scientists have been warning for years about something called reservoir-induced seismicity. Basically, all that water pressing down on the earth can trigger quakes on its own. There's another problem too: landslides. When the water level in the reservoir rises, it loosens the soil around the edges. Since the reservoir was filled, there have now been dozens of major landslides, some so powerful they've caused waves inside the reservoir itself. In one case, tens of thousands of cubic meters of earth and rock came crashing into the water in seconds. Imagine what that could do if the landslide happened right near the dam wall. Even though Chinese officials monitor the dam closely and carry out maintenance and inspections, some experts have pointed out that the original construction may not have been perfect. One hydrologist, Wang Weilo, raised red flags about how the design, construction, and inspection were all handled by the same group. He warned that cracks, rushed schedules, and poor quality materials could come back to haunt the structure down the road. So now we're left with this picture: an aging mega dam holding back one of the largest reservoirs on Earth, sitting in a place prone to earthquakes, dealing with increasing sediment buildup, surrounded by unstable slopes, and facing stronger and more unpredictable storms every year. It hasn't failed yet. But if something went wrong, even one thing, it could be the beginning of a chain reaction, and once that chain starts, there may be no way to stop it. Next, we're going to break down exactly how that failure might unfold. For Dinaos, the conditions that would line up, the timeline of collapse, and what cities would be hit first. It's not just about whether it could happen, no what. It's about how fast, how far, and how horrifying it really could be. It's easy to look at the Three Gorges Dam and just see strength. After all, we're talking about a wall of concrete that's over 2,300 meters long and about 185 meters high. But behind all that concrete is a system that's constantly under stress: physical, environmental, and human. It's a complicated machine built into one of the most unpredictable rivers on Earth. And the truth is, there's a long list of ways things could start to unravel. Let's start with one of the biggest concerns: seismic activity. The dam is built in a region of China that sits on several fault lines. Normally we think of earthquakes as something that just happens out of nowhere, but in this case, the weight of the reservoir itself, billions of tons of water pressing down on the Earth, can trigger what's called reservoir-induced seismicity. That means earthquakes that wouldn't normally happen might occur just because of the stress the water puts on the crust beneath it. Some scientists believe that dozens of small tremors recorded in the region since the reservoir was filled are likely linked to this exact phenomenon. A small quake might be manageable, but a big one, even just in the wrong spot, could push the structure past its limits. There's also the issue of landslides. Ever since the water level rose behind the dam, the steep terrain along the reservoir has been eroding. That's not just theory, there have been real events already. In May of 2009, huge chunks of land slid into the water at Wuxia Gorge, sending shock waves across the surface. In the first few months of 2010 alone, nearly 100 major landslides were reported in the reservoir zone. That might not sound like a direct threat to the dam, but the sediment and debris from those landslides flow toward the dam, slowly clogging the reservoir. That raises water levels, increases pressure on the structure, and decreases the amount of water it can safely hold during floods. Over time, this puts the entire system into a tighter and tighter corner. Now let's talk sediment. The Yangtze River has always carried a massive load of silt and mud. Before the dam was built, much of that sediment flowed downstream naturally, keeping the river's ecosystem in balance and reinforcing the riverbanks all the way to the coast. But now, most of that sediment settles in the reservoir. In fact, estimates suggest that about 40 million tons of sediment pour into the dam each year. With slower water flow above the dam, there's nowhere for it to go. It just builds up. That buildup doesn't just reduce capacity, it shifts water pressure onto different parts of the dam and alters how water flows through its turbines and spillways. The result is a system that's constantly adjusting to an ever-changing internal load, and that kind of pressure over time wears things down. Then you've got aging materials. The main dam was structurally completed in 2006, but that doesn't mean it was left alone. In fact, the full power station only became fully operational in 2012. And the final part of the project, a massive ship lift, wasn't finished until 2015. That means different parts of the structure were completed at different times, and they've been weathering the elements for over a decade now. Concrete expands and contracts with heat and cold. Steel corrodes, seals degrade. It all adds up over time. Engineers inspect and maintain the dam constantly, but some experts have raised concerns that early construction might not have met the highest standards. Hydrologist Wang Weilo, one of the loudest voices of criticism, has even claimed there were signs of cracking during construction and possible issues with concrete quality. These claims haven't been confirmed by the government, but they add to the worry that not everything behind the scenes is rock solid. One of the more delicate balancing acts the dam has to manage is between energy generation and flood control. When the reservoir is full, the dam can generate its maximum output of electricity. But in flood season, the water level has to be lowered ahead of time to create space for incoming rain. That trade-off creates a constant back and forth between power production and safety. If heavy rains come sooner or harder than expected, the operators might not have enough time to lower the reservoir, and that could raise the risk of overtopping, where water spills uncontrollably over the top of the dam. Even though the dam is equipped with emergency spillways, a sudden surge, say from a failed upstream dam or a monster storm, could overwhelm the system. And extreme weather isn't just a possibility anymore. Climate change is pushing rainfall patterns into new territory. The summer of 2020 saw record-breaking floods in China, pushing the Three Gorges Dam to its limits. The water level rose to over 165 meters, very close to its designed maximum of 175 meters. In response, authorities opened floodgates, unleashing flows of more than 70,000 cubic meters per second to try and lower the pressure. But with each flood season, the margin for error seems to shrink. And this year, June of 2025, weather forecasts are predicting another season of intense rainfall. Engineers are already working to lower the reservoir, but no one knows if that will be enough. So, when you put it all together, earthquakes, landslides, sedimentation, aging infrastructure, and increasingly extreme weather, you can start to see how a chain reaction might begin. The dam doesn't have to fail in one big moment. It could be a slow buildup of smaller issues, stacking up until something finally gives, and if it does, the next part of the story begins. What happens when a wall of water starts racing toward some of the most populated cities on Earth? That's what we'll explore next. If the Three Gorges Dam were to collapse, the destruction would be unlike anything China or the world has ever seen. This isn't just a local disaster. This would be a chain reaction of flooding, infrastructure failure, and mass displacement on an unimaginable scale. To understand how devastating it could be, we have to follow the water step by step, city by city, hour by hour. The first to be hit would be Yicheng, the city closest to the dam. Yicheng sits less than 40 kilometers downstream. Within minutes, a wall of water tens of meters high could crash into its streets, wiping out homes, power lines, and transportation routes. Most residents would have little or no time to escape. Bridges would collapse. Roads would vanish under waves of debris-filled water. The force of that initial surge could be enough to destroy every structure in its path. But the water wouldn't stop at Yicheng. It would keep moving downstream, building momentum as it rushed through the Yangtze River basin. Within hours, the flood could reach Jingzhou, a historic city with a population of over 5 million people. Much of Jingzhou lies on flat land near the river. That geography means slower drainage and deeper flooding. Even if early warnings were issued, evacuation would be chaotic, transportation would be overwhelmed, and low-lying neighborhoods could be completely submerged. Next, the water would bear down on Wuhan. This is not just a large city, it's a megacity. Over 11 million people live in Wuhan, and it's a key hub for finance, transportation, and technology. 3 major rivers, including the Yangtze and Han, converge there. If floodwaters from upstream hit Wuhan at the same time as heavy local rainfall, the result would be catastrophic. Subways would flood, the airport would be rendered useless, power stations, water treatment facilities, and hospitals could all be knocked offline. Rescue efforts would be nearly impossible in the early hours, and tens of thousands of lives could be at risk. The damage would continue far beyond Wuhan. Cities like Zhejiang, Nanjing, and even Shanghai, over 1,000 kilometers away, could feel the effects. While the force of the water would weaken over that distance, the volume would remain staggering. In lower areas, floodwaters could spread across vast swaths of farmland, drowning crops and displacing rural communities. Ports and industrial zones along the Yangtze River would be paralyzed. Highways and railway lines would be washed out. The cost to China's economy alone could stretch into the trillions of dollars. One of the most devastating long-term effects would be the collapse of the interconnected dam and levee systems along the Yangtze River. The Three Gorges Dam is part of a larger network of over 100,000 dams across the country, many of which are smaller and older. If the Three Gorges Dam failed, the flood would likely breach several of these structures as it surged downstream. Each failed dam would release more water, compounding the disaster and spreading it wider. Entire provinces could see their water systems permanently altered. And then there's the human cost. Conservative estimates suggest that over 400 million people live within the greater Yangtze River basin. Even if only a fraction of those people were directly affected, we're still talking about tens of millions displaced. Millions more could face shortages of clean water, food, and shelter. Disease outbreaks, especially in overcrowded evacuation centers, would be a serious risk. With supply chains cut and medical infrastructure damaged, emergency response teams would struggle to keep up. It would take weeks, possibly months, for aid to reach all the areas in need. Environmental damage would be another hidden but massive problem. The reservoir behind the Three Gorges Dam contains not only water, but also industrial runoff, sewage, and heavy metals that have settled there over years. If the dam failed, all of that would be swept downstream. Toxic materials could contaminate farmland, rivers, and coastal waters. The Yangtze River Delta, one of China's most fertile and economically vital regions, could be poisoned for years to come. In global terms, the collapse of the Three Gorges Dam would also disrupt international trade. Ports like Shanghai and Ningbo handle a significant percentage of China's exports. If those ports were flooded or cut off from rail and road transport, it would affect supply chains around the world. Factories would shut down. Prices for electronics, clothing, machinery, and other goods would spike globally. The economic ripple effect would be felt in Europe, North America, Southeast Asia, and beyond. But beyond all the statistics and projections, The heart of the tragedy would be the human stories. Families separated, entire neighborhoods erased, generations of history drowned in minutes. In many ways, the Three Gorges Dam was built to protect people from exactly this kind of nightmare. But if it were to fail, it wouldn't just be a collapse of concrete, it would be a collapse of trust, of planning, and of an entire way of life for millions. In the next part, we'll explore how prepared China is for such a worst-case scenario, and whether the systems in place today would be enough to stop the unthinkable from becoming reality. When it comes to the potential collapse of the Three Gorges Dam, the Chinese government has not been silent. There are emergency plans in place, but whether they are enough is another question entirely. A structure as massive and consequential as this demands a coordinated and layered defense system. Yet even with decades of planning, some cracks cannot be patched with paperwork alone. First, it's important to understand what kind of monitoring and early warning systems are already active. The Three Gorges Dam is equipped with thousands of sensors that measure pressure, stress, water levels, and seismic activity. These sensors transmit real-time data to control centers in Yichang and Beijing. Engineers claim that the dam can withstand earthquakes up to magnitude 7 and has overflow spillways designed to reduce pressure during extreme flooding. But no amount of data can offer total certainty. If the dam fails suddenly due to sabotage, a landslide, or a rare upstream earthquake, these systems would only provide seconds or minutes of warning to those in the path of destruction. Beyond the dam itself, China has developed a tiered emergency response structure. This includes local, provincial, and national crisis management teams. In theory, evacuation plans are regularly reviewed and practiced in some downstream cities. Large urban centers like Wuhan and Nanjing have contingency plans that include siren alerts, emergency broadcasts, and designated evacuation routes. Drones, satellite imaging, and even artificial intelligence tools are being used to track weather patterns and detect potential structural anomalies, but planning does not always translate into execution. One of the main challenges is geography. The areas most at risk lie along the Yangtze River, one of the most densely populated river basins on Earth. Some villages and towns are isolated or surrounded by mountains, with only narrow roads in and out. In such places, evacuation efforts could be delayed by traffic, poor communication, or landslides triggered by heavy rain. In larger cities, roads are often congested even during normal times. A mass evacuation of millions within a few hours is nearly impossible. There is also the question of political control. The Chinese government tightly manages public information. In the past, warnings about structural issues with dams or floods have been delayed, downplayed, or withheld altogether to avoid public panic. During the 2021 floods in Zhengzhou, for example, official reports did not fully capture the severity of the disaster until after the worst damage had occurred. If a similar pattern of secrecy happened during a Three Gorges emergency, valuable time could be lost, time that could save lives. In addition, while the Three Gorges Dam is the largest hydroelectric project in the world, China has over 98,000 other dams, many of them smaller, older, and more vulnerable. These dams form a cascading system of water control. If the Three Gorges Dam were to fail, that would place immense pressure on this entire system. The failure of even a handful of secondary dams downstream could make the disaster significantly worse, and unlike the main structure, many of these smaller dams are not as well monitored or maintained. On top of all this, military assets would likely be mobilized in the event of a collapse. The People's Liberation Army has rapid response units trained for flood rescue and logistics. Boats, helicopters, and temporary shelters could be deployed to major cities and evacuation zones, but again, scale is the issue. It is one thing to rescue thousands, it is another to respond to tens of millions needing aid all at once. If supply chains are broken, bridges washed away, and power grids offline, even the best equipped teams will struggle. China has made some efforts to improve community-level preparedness in schools and factories. Some citizens undergo annual emergency drills. Government apps can push evacuation alerts directly to smartphones. Civil defense shelters have been converted in some regions to handle flood refugees, yet access to these resources is uneven. Many rural areas still lack digital infrastructure or reliable emergency communication. International cooperation is also limited. Due to political tensions and national security concerns, the Chinese government does not openly share structural data on the Three Gorges Dam with other nations. This makes outside assessment difficult and hinders offers of international assistance. If the dam were to fail, countries downstream, especially those reliant on Chinese supply chains, would receive little advance notice or coordination. One key blind spot in China's emergency planning is environmental fallout. While the focus has largely been on water and human evacuation, there is less clarity on how the government would contain chemical spills or manage water-borne diseases in flooded areas. Large-scale flooding often causes sewage overflow, industrial leakage, and hazardous contamination. In the chaos of mass displacement, it is unlikely that environmental mitigation would be prioritized. In short, China has systems in place to monitor, respond to, and possibly manage a dam-related emergency, but none of them have ever been tested at the scale of a complete Three Gorges failure. Even with the most advanced technology, fastest troops, and strictest planning, the sheer size of the population and the speed at which such a disaster would unfold leave a terrifying question. Would any of it be enough? In the final part, we will examine the long-term consequences of a collapse, not just for China, but for the world. From food security and energy disruption to political fallout and global markets, the failure of this dam would echo far beyond the riverbanks. If the Three Gorges Dam collapsed, the devastation would not stop at China's borders. What begins as a physical disaster could rapidly spiral into an economic, environmental, and geopolitical crisis on a global scale. In this final part, we look beyond the immediate flood zones to explore how the world might feel the shockwaves of a failure that would alter global systems overnight. To begin, China plays a central role in the global economy. It is the world's largest manufacturing hub and the largest exporter of goods. The Yangtze River Basin is home to more than 400 million people and contributes more than 40% of the country's GDP. Major industrial cities like Wuhan, Chongqing, and Nanjing rely heavily on the transportation, water, and power infrastructure connected to the dam. If that infrastructure is destroyed, it would trigger an immediate collapse in manufacturing output, especially in electronics, automotive parts, and heavy machinery. The supply chain disruption would be massive. Ports and railways in the region would be paralyzed. Global companies that depend on Chinese factories, ranging from consumer tech brands to pharmaceutical giants, would experience immediate shortages. Products could disappear from shelves around the world within weeks. Shipping delays would skyrocket. Prices on raw materials and finished goods would spike, contributing to inflation in already fragile global markets. The energy impact would also be severe. The Three Gorges Dam is the single largest hydroelectric power station in the world. If it fails, its massive contribution to China's grid, around 2% of national energy, would vanish. While this percentage may sound small, it supports critical infrastructure in eastern and central China, including power for hospitals, water treatment plants, and communication systems. Rolling blackouts could follow across several provinces, straining emergency response and industrial recovery. Environmental consequences would not be limited to floodwaters. The Yangtze is a vital artery for agriculture and ecology. Its basin supports rice, wheat, and fish production for hundreds of millions. A sudden collapse would destroy crops, spread industrial toxins from submerged factories, and kill off entire aquatic ecosystems. This could lead to long-term food shortages within China and affect global food trade, particularly in Asia and Africa, where Chinese agricultural exports are critical. International financial markets would react instantly. Investors often respond to disasters with panic, and a collapse of this scale would send shockwaves through stock exchanges in Hong Kong, Tokyo, London, and New York. China's currency could fall, foreign investment could stall, and insurance firms with exposure to Chinese assets would face massive payouts. The economic ripple effect would likely trigger recessions in multiple countries, especially those closely tied to China through trade or debt. Then there's the political dimension. A collapse of the Three Gorges Dam would be seen not just as a natural disaster, but as a national failure. It is one of China's proudest infrastructure achievements, a symbol of power, progress, and engineering superiority. If it failed, the Chinese Communist Party could face intense public backlash. Protests could break out, especially if the government was seen as hiding information or mishandling the response. In the worst-case scenario, such a collapse could threaten internal political stability. Internationally, tensions could rise. Neighboring countries downriver, such as Vietnam, might demand answers or compensation if they are affected by flooding, or water shortages, some nations may accuse China of negligence or failing to maintain a project with global consequences. At the same time, geopolitical rivals might exploit the chaos to gain influence or negotiate more favorable trade terms. Cyber attacks, misinformation campaigns, and border tensions could all increase as a result. Humanitarian aid would become another flashpoint. If China requested or accepted international assistance, questions would arise about coordination, transparency, and access. Foreign governments and NGOs may be hesitant or restricted in what they are allowed to do. The sheer number of displaced people, possibly tens of millions, would overwhelm aid systems, and China might be forced to prioritize urban recovery over rural survival. This would raise serious ethical concerns and could strain relations with other countries already dealing with global refugee crises. In the long term, the collapse would permanently reshape how nations view megaprojects and large-scale dams. For decades, the Three Gorges Dam has been cited as an example of engineering ambition. Its failure could chill future hydroelectric investment, trigger stricter international engineering codes, and increase skepticism of top-down infrastructure development. At the same time, countries may double down on decentralizing power grids and water management systems to avoid similar catastrophes. Ultimately, the failure of the Three Gorges Dam would be more than a Chinese disaster. It would be a global turning point. From the floodplains of central China to the trading floors of distant financial capitals, every corner of the world would feel its impact. Whether through broken supply chains, rising prices, shifting alliances, or the haunting image of a drowned megastructure, the collapse would mark the end of one era and the start of something far less stable. Earth's magnetic field isn't just a scientific curiosity, Bao. It's a crucial part of what makes life on this planet possible. Generated deep beneath our feet in the outer core, this protective force emerges from swirling molten iron and nickel nearly 2,000 miles below the surface. The constant motion of this superheated liquid metal generates electric currents, which in turn produce Earth's global magnetic field, a geodynamo that has been running for billions of years. This magnetic field creates what's known as the magnetosphere, an enormous teardrop-shaped shield that extends tens of thousands of miles into space. Its job? To deflect charged particles from the solar wind and cosmic rays that constantly bombard our planet. Without this magnetic shield, Earth's atmosphere would gradually be stripped away by solar radiation, much like what happened on Mars billions of years ago. In other words, Earth's magnetic field is not just invisible, it's indispensable. But lately, scientists have noticed some unusual behavior. The most visible sign of this turbulence is the dramatic movement of the magnetic North Pole. For centuries, the North Magnetic Pole drifted gently through the Canadian Arctic. Then in the late 20th century, its speed began to increase. By the mid-1990s, it was moving about 9 miles per year. But by the early 21st century, it had accelerated dramatically to speeds between 34 and 37 miles per year, a rate 4 times faster than previous averages. Though that speed has recently slowed to around 22 to 31 miles per year, the overall trend remains clear. It's headed rapidly towards Siberia. This movement isn't just a scientific footnote. It has forced international agencies to update critical navigation systems more frequently. The World Magnetic Model, which underpins everything from smartphone compasses to military navigation tools, required an unexpected update in December of 2024 due to the pole's erratic sprint. But pole movement isn't the only concern. Earth's magnetic field itself is weakening. Measurements taken since the early 19th century show a decrease of about 9 to 10% in the field's global strength. And when scientists dig deeper into the geological record, they find that this decline may be even more pronounced, potentially a 30% drop over the last 3,000 years. One especially alarming feature is the South Atlantic anomaly, a vast region stretching from South America to Southern Africa, where the magnetic field is significantly weaker. In this zone, satellites are exposed to increased levels of radiation and are more prone to malfunctions. The Hubble Space Telescope and other satellites often power down sensitive instruments when passing through it. This weakening is not uniform, it's patchy, complex, and hard to predict. The magnetic field's behavior isn't random, it's the result of shifting patterns in the fluid outer core. Scientists believe 2 large magnetic regions under Canada and Siberia are locked in a kind of subterranean tug of war, influencing the position and movement of the magnetic poles. Right now, Siberia's magnetic region appears to be winning, hence the rapid movement of the pole in that direction. While all of this may sound apocalyptic, It's worth noting that changes in the magnetic field are not new. Earth's magnetism is naturally dynamic. The problem is that we're now starting to detect large-scale changes over human timescales, not over millions of years, but over mere decades. And this opens the door to much deeper questions. What happens if the weakening continues? Could it signal an impending magnetic reversal? Could it affect our technology, our climate, or even our biology? That's where we'll head next. So now that we've broken down the weird behavior of Earth's magnetic field, let's talk about what's really on the line. Because while the idea of a magnetic field collapse might sound abstract, the impacts would be anything but. This isn't just a science fiction scenario. If the field continues to weaken or goes into a full reversal, the fallout could hit every layer of modern civilization, from satellites in orbit to ecosystems on the ground. Let's start in space. Satellites, which form the backbone of global communication, navigation, and surveillance, are extremely vulnerable to radiation. Earth's magnetic field acts like a protective dome, deflecting charged particles from the sun. Without it, or even with it weakened, those satellites are exposed to intense solar and cosmic radiation. This isn't theoretical. We already see it happening in a region called the South Atlantic Anomaly. In that part of the world, the magnetic field is so weak that satellites passing through it often experience memory glitches or suffer from electrical failures. Engineers have to program some satellite systems to shut down temporarily while passing through this zone to prevent damage. Now imagine that anomaly expanding globally. Without adequate shielding, satellites in low Earth orbit would degrade much faster. Global positioning systems, satellite phones, weather forecasting tools, and internet access through orbital networks like Starlink could all become unreliable or fail altogether. And these systems are no longer just conveniences. They run everything from international finance to emergency services and air traffic control. But the risks don't stop in orbit. Power grids on the ground are also in the danger zone. When geomagnetic storms interact with Earth's magnetic field, they can induce electrical currents in long conductors like power lines. Under normal conditions, the magnetic field buffers a lot of that energy, but if it weakens or if a reversal causes temporary disruptions in the field's structure, the energy from solar storms can surge into power grids with little resistance. A striking example of this occurred in March of 1989, when a geomagnetic storm, triggered by a solar flare, caused the entire power grid in Quebec, Canada to collapse. In less than 2 minutes, 6 million people were plunged into darkness. That storm happened under normal magnetic field conditions. If the field were weaker, a similar event could cause continent-wide blackouts, destroying high-voltage transformers that would take months or even years to replace. The economic cost would be staggering, but the human impact, hospitals without power, food supply chains disrupted, no communications, could be far worse. And then there's the biological angle. The magnetic field helps protect living organisms from genetic damage caused by cosmic radiation. With less protection, life on Earth, including humans, would be exposed to higher doses of ionizing particles. Over time, this exposure could lead to increased cancer rates and greater risk of developmental mutations in both humans and wildlife. While our atmosphere would still provide some shielding, high-altitude regions and areas near the poles, where radiation already penetrates more easily, would be hit hardest. Some scientists believe that during past geomagnetic excursions or reversals, early humans adapted their behavior in response to these increased radiation levels. There's evidence that ancient humans began using caves more frequently, potentially as a form of shelter from solar activity. In modern times, however, we depend on technology and global systems far more than our prehistoric ancestors did, and those systems are far more fragile. Even animals would struggle. Many migratory species like whales, birds, sea turtles, and bees rely on the magnetic field to navigate. They sense magnetic lines almost like a compass to guide them across vast distances. If those lines become distorted, these species could become disoriented, lose their migration paths, or stop reproducing effectively. Entire ecosystems could destabilize, especially in the oceans, where magnetic navigation plays a critical role for both predators and prey. And while some impacts, like atmospheric erosion gusto, would take an incredibly long time to fully develop, they are not impossible. Scientists believe that Mars once had a magnetic field similar to Earth's, but after it disappeared billions of years ago, the solar wind began stripping away its atmosphere, turning it into the dry, lifeless world we see today. While Earth's gravity and remaining atmospheric pressure would slow that process here, a significantly weakened field over many thousands of years could open the door to long-term atmospheric loss, with consequences no one can fully predict. In short, the magnetic field isn't just a fascinating part of Earth's inner workings. It's a critical piece of the puzzle that makes life seem Kuro and civilization near possible. As it weakens and shifts, we're not just watching a natural process unfold. We're potentially witnessing the slow unraveling of protections we take for granted every day. So how do we know all of this is happening? How can scientists tell that Earth's magnetic field is weakening, or that it might reverse in the future? The answer lies in a mix of space-based monitoring, geological records, and some pretty remarkable physics. This part of the story is not about guessing. It's about hard data and long-term observation. The first tool scientists use is satellite data. Since the early 2000s, a number of satellites have been launched specifically to monitor the strength and structure of Earth's magnetic field. The most advanced of these is the European Space Agency's SWARM mission, launched in the year 2013. SWARM consists of 3 identical satellites, flying in formation around the planet. They continuously measure the magnetic signals coming from Earth's core, mantle, crust, oceans, and even the ionosphere and magnetosphere. These measurements are incredibly precise, allowing scientists to map how the field changes in both space and time. What they've found is consistent with earlier predictions. The field has been steadily weakening, especially in a large region stretching from South America to Southern Africa, known as the South Atlantic Anomaly. In just the past 200 years, the global magnetic field has weakened by roughly 10%. But within the anomaly, the weakening has been far more rapid. This real-time monitoring is only part of the picture. To understand what might happen next, scientists also look backward, deep into Earth's geological past. They do this by studying volcanic rocks, ocean floor sediments, and even ancient clay pots. When molten lava cools, or when sediments settle, tiny magnetic particles inside them align with Earth's magnetic field at that moment. Once locked in place, those particles become permanent records of the planet's magnetic orientation and strength. These fossil magnets can be dated using radiometric techniques. Over the past several decades, this kind of research has revealed that Earth's magnetic field has reversed many times in its history. On average, it flips about once every 200 to 300,000 years. The last full reversal, known as the Brunhes-Matuyama reversal, happened roughly 780,000 years ago. That means we are long overdue by historical standards, though the field does not flip on a schedule. And what's even more interesting is that magnetic reversals don't happen overnight. Evidence shows they can take anywhere from 1,000 to 10,000 years to complete. During this time, the field becomes disorganized and weakens significantly. Magnetic north and south can wander unpredictably or even appear in multiple places at once. And that's exactly what's concerning scientists now. Magnetic north has been shifting at an accelerated rate since the early 20th century. It used to move around 10 kilometers per year. Now it's racing across the Arctic at nearly 50 kilometers per year. This movement has forced regular updates to navigation systems, including the World Magnetic Model used by everything from smartphones to military aircraft. At the same time, complex computer models of Earth's core, powered by supercomputers and guided by satellite data, are showing signs of increasing turbulence in the outer core, where the magnetic field is generated. This turbulence doesn't guarantee a reversal, but it aligns with what we would expect to see in the lead up to one. Some scientists believe we may already be entering the early stages of magnetic excursion, a short-term disruption where the field weakens and shifts significantly without a full reversal. To be clear, there is still debate within the scientific community. Some researchers argue that we are simply seeing a natural fluctuation and that the field could stabilize again. Others warn that the current trend fits the pattern of past reversals and should be taken seriously, but no one is ignoring it. In fact, global magnetic monitoring has become a top priority for organizations like NASA, the European Space Agency, and geological institutes around the world. These groups are constantly updating models and issuing data to industries that rely on accurate magnetic positioning. So while we don't know exactly when or if a full reversal will happen, we're watching closely. The warning signs are real, the data is solid, and the consequences, as we've already seen, could be massive. What comes next might not be a sudden flip, but a long, messy period of change, and we may already be in the middle of it. If Earth's magnetic field suddenly vanished or flipped completely, life would not end. But the modern world as we know it would face serious challenges. This isn't about fireballs or earthquakes. The danger lies in something invisible but powerful: radiation from space. Earth's magnetic field acts as a giant shield, protecting us from solar winds and cosmic rays. Without it, that radiation would have a much easier time reaching the surface. One of the first and most immediate effects would be in the upper atmosphere. The magnetic field currently helps trap charged particles in radiation belts high above Earth, keeping them away from the surface. If the field weakened significantly, the solar wind could strip away parts of the atmosphere, especially the outer layers that contain ionized gases. While this would take time, it could increase our exposure to ultraviolet and high-energy radiation. The threat is even more immediate for satellites and spacecraft. Without a strong magnetic field, satellites in low Earth orbit would be far more vulnerable to damage from solar storms. Communication systems, GPS navigation, weather tracking, and military surveillance all depend on those satellites. A strong geomagnetic storm, similar to the one that hit Earth in the year 1859, known as the Carrington event, could fry entire networks and cause global blackouts. That event happened under normal magnetic conditions. Imagine the damage during a field reversal or collapse. Astronauts would be at greater risk as well. The International Space Station is still within Earth's protective field, but during a weakened period, that protection would shrink. Without additional shielding, astronauts could be exposed to harmful levels of radiation. Space agencies would have to delay missions or invest heavily in radiation-hardened technologies. On the ground, power grids would also be at risk. Changes in the magnetic field can induce electric currents in long conductors like transmission lines and pipelines. During past geomagnetic storms, some power systems experienced voltage irregularities, transformer failures, and blackouts. In 1989, a geomagnetic storm knocked out power in Quebec, affecting millions of people. That was a relatively minor event. A weakened or chaotic magnetic field would make these disruptions more frequent and severe. Migratory animals would face confusion too. Many species, such as birds, whales, and sea turtles, rely on Earth's magnetic field to navigate long distances. Studies have shown that some animals have magnetoreceptors in their brains or beaks that allow them to sense magnetic fields. A sudden change or reversal could throw off migration patterns, disrupt breeding seasons, and even cause population declines. Air travel could also be impacted. Polar flight routes, which pass through areas where the magnetic field is already weaker, would be more dangerous during solar storms. Airlines might have to reroute flights to avoid increased radiation exposure to passengers and crew, which would lead to longer travel times and higher fuel costs. And then there's human health. While Earth's atmosphere still offers protection from most radiation, a weaker field would let more high-energy particles reach the surface. Over time, this could slightly increase rates of cancer or genetic mutations, especially in people living at higher altitudes or closer to the poles. While the risk wouldn't be catastrophic, it's something scientists are actively studying. One lesser-known issue involves the technology that depends on magnetic orientation. Everything from smartphones to drilling equipment to submarines relies on magnetic data. During a field reversal, magnetic north would shift unpredictably. Compasses could become unreliable, and navigation systems that depend on magnetic input would need constant recalibration. This would affect shipping, military operations, and even underground mapping. Importantly, the effects of a full reversal wouldn't happen overnight. The transition could take hundreds or even thousands of years. During that time, the magnetic field would likely weaken, fluctuate, and form multiple poles before finally stabilizing. But this slow process doesn't mean the impacts would be easy to manage. Our infrastructure, communication networks, and global navigation systems were all built during a period of magnetic stability. We have no precedent for how to operate in a world where the field is shifting rapidly beneath our feet. In short, a magnetic collapse or reversal wouldn't destroy life, but it would challenge nearly every system our modern world depends on, from power and communication to transportation and navigation. While Earth has survived many reversals in the past, the stakes are higher now than ever before. The question isn't whether the planet can endure it. The question is, are we ready for it? If Earth's magnetic field reversed or significantly weakened, survival would depend not only on nature, but also on how well humanity prepares in advance. While we can't stop a geomagnetic reversal from happening, we can take real, concrete steps to reduce the impact on our technology, infrastructure, and health. First, let's look at forecasting. Scientists are already tracking changes in the magnetic field with high precision. The South Atlantic anomaly, a region where the field is particularly weak, has been growing and shifting westward. This anomaly poses increased risk to satellites and has drawn attention to the field's ongoing instability. With data from satellites like ESA's SWARM constellation and NASA's magnetospheric multi-scale mission, researchers can monitor these trends and spot signs of an impending shift. However, predicting exactly when a reversal might occur is still difficult. Earth's magnetic field is generated by the movement of molten iron in the outer core, and this geodynamo is complex and unpredictable. Some reversals in the past have taken as little as 1,000 years, while others took more than 10,000. There have also been failed reversals, where the field started to flip, but returned to its original state. This variability makes it hard to forecast the exact timeline or intensity of a future event. That said, there are steps we can take now to strengthen our resilience. One of the most critical areas is satellite design. Engineers are already working on developing satellites with stronger shielding against solar radiation. Space agencies are also exploring ways to reroute or power down satellites during major solar events to reduce damage. Having backup systems and redundancy in satellite networks would also help maintain communication and navigation during disruptions. On Earth, energy companies are beginning to study how geomagnetic storms interact with the power grid. Some are installing sensors and early warning systems to detect sudden spikes in ground currents caused by magnetic changes. Transformers and high-voltage systems can be built with protections that allow them to shut down safely instead of burning out. In areas like northern Canada or Scandinavia, where the field is naturally weaker, these protections could be especially valuable. Airlines may also need to rethink flight paths. During periods of high solar activity, polar flights could be redirected to lower latitudes to protect passengers and crew from increased radiation exposure. This has already been done during intense solar events in the past, and similar protocols would likely become more routine during a magnetic reversal. In the field of public health, medical researchers are beginning to study the long-term effects of increased radiation exposure. While Earth's atmosphere will still shield us from most of the sun's harmful rays, the added risk may lead to updated guidelines for radiation limits, especially for pilots, astronauts, and people living at high altitudes. Portable radiation sensors and protective materials could become more common in certain professions. Even navigation systems, both civilian and military, would require major adjustments. Modern aircraft, submarines, and shipping vessels often use magnetic compasses as backups to GPS systems. A magnetic reversal would force designers to rethink those systems or rely more heavily on non-magnetic alternatives. Military planners would also need to recalibrate long-range missile systems and battlefield navigation tools that use magnetic orientation. Education and public awareness could play an important role too. A magnetic reversal would not be a global catastrophe, but it could cause widespread confusion. Accurate, science-based communication would be essential to keep the public informed about risks and necessary precautions. Governments could release guidelines on how to respond to power outages, satellite failures, or navigation issues caused by a weakened field. In the longer term, some scientists have even proposed large-scale, space-based magnetic shields, giant structures that could help block radiation at key points between the Earth and the Sun. These ideas are still theoretical, but they reflect how seriously researchers are taking the potential risks of a magnetic collapse. Ultimately, while a full magnetic reversal would bring serious challenges, it would not be the end of the world. Life has survived dozens of magnetic flips over the past hundreds of millions of years. The difference now is that human society is built on fragile technology. Our survival won't depend on nature, it will depend on how seriously we take the warnings and how wisely we prepare for what's coming. A magnetic field reversal may be slow, silent, and invisible, but its consequences could be global. The best way forward is not fear, but readiness. Imagine an iceberg so vast, so heavy, it challenges the scale of entire cities. This is A23A, the largest iceberg currently drifting in the Southern Ocean, a true titan of ice weighing close to 1 trillion tons. But what makes this icy giant truly fascinating is its story. One of decades spent trapped beneath the frigid Antarctic seas. before finally breaking free to begin an epic and unpredictable journey. The 23A originated in 1986 when it calved from the Filchner-Ronne ice shelf, a massive floating extension of the Antarctic ice sheet. To visualize its size at birth, picture an area nearly twice that of Greater London, or comparable in size to the entire US state of Rhode Island. Its thickness is equally staggering, no less approximately 400 meters, or around 1,300 feet, taller than many of the world's tallest skyscrapers. This colossal frozen mass was effectively an ice island, grounded firmly on the seabed of the Weddell Sea for more than 3 decades, rendering it nearly motionless in the harsh Antarctic environment. An extraordinary historical tidbit highlights the iceberg's magnitude and significance. In 1987, a Soviet research station named Druzhnaya Thirst was positioned atop this colossal ice mass. The sudden shift of the iceberg triggered a tense rescue operation to relocate personnel and equipment from a drifting research base, a rare moment where human activity directly intersected with the slow-moving forces of Antarctic ice. The station's existence on such a slowly migrating iceberg exemplifies the immensity and inertial power of a 23A during its prolonged grounding phase. This period of immobility came to an end around 2020, when a 23A began to move once more. After more than 30 years locked in place, the iceberg awoke from its frozen slumber and commenced a slow, deliberate voyage northward. Satellite tracking and oceanographic monitoring, since then, have captured its gradual but steady drift into warmer and more dynamic waters. This marks the beginning of a dramatic new chapter for the iceberg and news, one that has fascinated scientists, environmentalists, and maritime observers alike. Understanding the physical forces behind this awakening involves delving into Antarctic oceanography. Changes in sea temperatures, shifts in currents, and melting at the iceberg's base all contributed to reducing the grounding friction that once held A23A firmly to the seabed. The thawing ice beneath effectively loosened its grip, allowing the immense mass to start moving. This process highlights the delicate balance between cold Antarctic waters and the slowly warming climate, influences that affect even the most massive and stable ice formations. Since its release, a 23A's journey has been anything but predictable. While icebergs naturally drift with prevailing currents and winds, the scale of this iceberg means its movement is influenced by complex interactions between ocean currents, underwater topography, and atmospheric conditions. The iceberg's sheer weight and size allow it to act almost like a floating continent, disrupting local water flow and creating unique microenvironments in its wake. Tracking A23A has required international collaboration, utilizing satellite imagery, aerial reconnaissance, and expeditions by research vessels. One notable encounter occurred in early December 2023, when the British polar research ship RS Sir David Attenborough navigated alongside the iceberg, providing scientists a rare opportunity to collect data directly from the surrounding waters. This allowed detailed study of the iceberg's impact on ocean chemistry, temperature gradients, and marine ecosystems. As we begin this exploration of a 23A's story, it is important to appreciate the iceberg not just as a massive block of ice, but as a dynamic natural entity. Its birth, decades of stasis, and sudden awakening are tied to the broader environmental forces shaping Antarctica and the Southern Ocean. This iceberg saga offers a unique window into the shifting balance of Earth's polar regions in a changing climate, a story of frozen power slowly coming to life. After spending over 3 decades grounded on the seabed of the Weddell Sea, the enormous iceberg A23A finally broke free and began its slow northward drift around the year 2020. This moment marked a significant shift in the iceberg story, from a frozen, stationary giant to an active voyager navigating the complex currents of the Southern Ocean. From the moment it started moving, scientists worldwide have been meticulously monitoring A23A's position and condition, using satellite imagery, radar systems, and oceanographic sensors. Its path has been anything but straightforward. Instead of a smooth journey, the iceberg's travel has been marked by stops, slow spins, and long pauses influenced by underwater topography and oceanic currents. By the end of November 2023, a 23A was spotted drifting near the northernmost tip of the Antarctic Peninsula, a critical waypoint before entering the wider Southern Ocean. This location is notable for strong winds and turbulent seas, which make navigation treacherous not only for ships, but for icebergs as well. A particularly remarkable event occurred on the 1st of December 2023, when the British polar research vessel, RRS Sir David Attenborough, sailed alongside this gigantic mass of ice. Despite traveling at roughly 10 knots, the ship took several hours to pass the iceberg's towering wall of ice, which rose over 400 meters from the sea surface. Scientists aboard took the opportunity to collect vital water samples and study the effects of such an enormous freshwater source on the surrounding seawater chemistry. Their research focused on how mineral dust embedded within the ice could nourish marine ecosystems once released through melting. Following this encounter, the iceberg's movement entered a fascinating phase during late 2024. It became trapped in a natural oceanic phenomenon known as a Taylor column, created when a strong current flows over an underwater mountain. In this case, the seamount called Pyrie Bank, near the South Orkney Islands, held the iceberg in place, causing it to rotate slowly and spin approximately 15 degrees counterclockwise each day. This spinning motion dramatically slowed a 23A's progress and showcased the incredible power of ocean currents and underwater landscapes on giant ice masses. Finally, in December 2024, the British Antarctic Survey reported that A23A had escaped the Taylor column's grip. Freed once again, it resumed its northward drift, now carried by the Antarctic Circumpolar Current. This massive current, often dubbed Iceberg Alley by oceanographers, acts as a natural conveyor belt, guiding icebergs through the Southern Ocean, but also funneling them toward more temperate waters where melting accelerates. Throughout this journey, researchers and ship crews have remained vigilant, aware that this slow-moving behemoth poses both scientific intrigue and practical challenges. Each twist and turn, every pause and spin adds to the unfolding narrative of a 23A's odyssey, a story of colossal forces at work beneath the surface of the world's southernmost ocean. As A23A progressed northward into the Southern Ocean's busy shipping lanes, concerns mounted among maritime authorities and environmental scientists alike. Unlike typical icebergs, which tend to be smaller and more predictable, this gargantuan iceberg measures roughly 550 meters at its widest point and extends nearly 2 kilometers in length. Its massive size creates a formidable hazard for vessels navigating the treacherous southern seas. Shipping companies operating in the South Atlantic, particularly those on routes between South America and the Antarctic research stations, have been closely tracking the iceberg's position using updated satellite data provided by the International Ice Patrol. This organization, established in the wake of the Titanic disaster, now employs advanced technologies like synthetic aperture radar to detect and monitor even the most remote icebergs. Because of A23A's enormous size, the iceberg cannot be diverted by small-scale currents or winds, making its trajectory challenging to predict. Ocean models forecast that by late 2025, the iceberg could drift into the Scotia Sea region, an area critical for both commercial fishing and scientific expeditions. Ships in this zone must be prepared to alter course significantly to avoid potential collisions. Beyond maritime safety, a 23A poses an ecological challenge. As it melts, the iceberg releases vast quantities of fresh water into the salty ocean, impacting local salinity levels. This sudden influx can disrupt ocean circulation patterns, which in turn affect nutrient cycling. Marine life, from microscopic plankton to larger species such as krill, depends on the delicate balance of these nutrients for survival. Studies conducted near other large Antarctic icebergs reveal that they can create oases of marine productivity by fertilizing waters with iron and other trace elements locked within the ice. However, the meltwater can also lower oxygen levels in surrounding waters, threatening sensitive species like the Patagonian toothfish, a prize catch in the Southern Ocean. In addition to ecological impacts, the iceberg's immense size means it carries enough fresh water to temporarily influence weather patterns. Meteorologists have noted that large icebergs can alter local atmospheric conditions by cooling the air above, sometimes triggering fog or low clouds, which pose additional hazards for aviation and sea navigation. Maritime authorities have increased the issuance of iceberg warnings and implemented more frequent aerial patrols over key regions. The South Atlantic Ocean, especially near the Falkland Islands and South Georgia, remains on high alert as A23A continues its slow approach. International cooperation between research institutes and naval forces is critical to ensuring safe passage for vessels and minimizing environmental damage. In sum, the journey of A23A is not only a natural spectacle, but a serious test of modern navigation, environmental science, and international coordination. The coming months will be decisive as this iceberg moves closer to increasingly busy waters, reminding the world of the enduring power and unpredictability of nature. As giant A23A continues its gradual drift, scientists are closely monitoring its long-term fate and what it reveals about the changing Antarctic environment. Icebergs of this scale are natural phenomena, but their frequency and behavior provide critical clues about climate trends. A 23A originated from the Run ice shelf, one of Antarctica's largest ice shelves, which has experienced increased fracturing over the last 2 decades. Since the year 2000, satellite observations indicate that ice shelves in the region have been thinning and retreating due to rising ocean temperatures and changing wind patterns. These changes contribute to more frequent calving events where huge chunks of ice break away, like the one that formed A23A in late 2022. Experts warn that the iceberg's size, while remarkable, is part of a growing pattern of large ice masses breaking free more often. This phenomenon is linked to the broader consequences of global warming, where Antarctic ice sheets are losing mass at an accelerating rate. Research published in recent years estimates that the continent is losing approximately 150 billion metric tons of ice annually, contributing to rising global sea levels. The eventual melting of A23A will add to freshwater input in the Southern Ocean, with unknown long-term effects on ocean circulation and marine ecosystems. While this iceberg's presence may temporarily alter local conditions, the cumulative effect of melting Antarctic ice globally is far more significant. Scientists are particularly concerned about the potential weakening of the Antarctic circumpolar current, which plays a key role in regulating Earth's climate by distributing heat and nutrients. Moreover, large icebergs like A23A can influence research and logistics in Antarctica. They may obstruct supply routes to research stations or alter local ice conditions, requiring adjustments in expedition planning. Authorities are investing in enhanced monitoring technologies to anticipate these impacts better and maintain safety in the region. Looking ahead, the path and longevity of A23A remain uncertain. Some models suggest it could persist for several years, slowly breaking into smaller fragments as it moves northward, while others predict it may melt completely within 1 to 2 years depending on ocean temperatures. Regardless, this iceberg has already captured worldwide attention, symbolizing the dynamic and fragile state of our planet's polar environments. In conclusion, giant A23A is more than just a drifting ice mass. It is a vivid reminder of Earth's evolving climate and the complex interplay between ice, ocean, and atmosphere. Its journey will continue to be closely watched by scientists and policymakers alike as they seek to understand and respond to the challenges posed by a warming world.